Walter. He currently is a professor at the Ruhr University in Bochum, but I guess we all know him from his time here at QSoft when he was roaming the hallways here at NWO-I. And before that, he was a postdoc in Stanford University, and he did his PhD at ETH in Zurich. And Michael has a really broad interest in several topics in the area of quantum information. And he has really ranging from actually implementations and wondering about programming and software development to the holographic principle and ADS-CFT correspondence in theoretical physics, understanding string theory and quantum gravity. Also, he has worked on the theory of entanglement, and also in deep problems in mathematics concerning representation theory, Kronecker coefficients, and Lie groups. And also he has worked on tensor scaling together with Avi here. And he was also awarded the Royal Dutch Academy of Arts and Sciences Early Career Award, and he recently obtained an ERC starting grant. And it's my great pleasure to give the floor to Michael.
Thanks very much. Thanks very much for the kind invitation, for the kind words. Yeah, it's going to be fantastic. It's very flattering, slightly humbling to speak at this occasion. So the topic I chose for today's talk is I want to discuss symmetries in computational problems, how those symmetries help us tackle those problems using ideas from optimization theory. And this is sort of a very fitting work because indeed what I'm describing here is work by Avi and collaborators. So I'm just one of those. Yeah, so I suppose we can, well, slides allowing, jump right into it. So I want to start the talk just with sort of an appetizer, then sort of systematize things and give you sort of a panorama of some developments that we've been engaged in combining symmetries and optimization. And so this is the appetizer, the prelude. And it's a very simple problem, simple computation problem. So suppose we have a matrix with non-negative entries, X. Then we say scaling of this matrix is simply another matrix that we get by rescaling all the rows by some numbers AI and rescaling all the columns by some number Bj. Okay. And then another definition that we want, so that's the definition of a scaling. Another definition that we like is we say matrix doubly stochastic if its row sums are all 1 and if its column sums are all 1. Okay. So these are nice definitions. Maybe it's not exactly clear why we look at them. But we want to study a problem called the matrix scaling problem. And what this problem asks is, suppose I take an arbitrary such matrix X, can I rescale the rows and columns in such a way to turn this into a doubly stochastic matrix? Okay. And there's many reasons why you might like to do such a thing. Maybe you have a table of data, you want to normalize it, sort of remove all information about the individual population, sort of focus on the correlations. That was just one, that's a statistics motivation. There's many more motivations, okay. And it seems like a pleasant problem, but it's not so clear how to attack it. So here's a silly way of doing it. Well, it's easy to make all the row sums equal to 1. We simply divide each row by its sum, right? Then it's 1. It's also easy to make the column sums equal to 1. And what's amazing is, and that's a procedure known as Synchron's algorithm, flip-flop, iterative proportional fitting, lots of names, discovered many times. So it's exactly this procedure. We start with a matrix, say this one, now we normalize the rows. So we divide the first row by 3, the second by 4, we get this one, now we normalize the columns, then the rows, and so on and so forth. And the amazing thing is that this works, okay? So it converges not only in that example, right? So in this example, we get a matrix that's as close to doubly stochastic as we like. But it works always. It works always when it is possible. And even the algorithm is efficient, okay? And there's many reasons why I want to introduce this. One, of course, is that this analysis was done by Avi and collaborators. And sort of, in some sense, in retrospect, kicked off this entire investigations that we are going to discuss today. Now, there's more that one can say. There's actually lots more about this problem that we won't be able to say today. One thing I want to say is, well, so here I wrote, so this procedure works whenever it's possible. It would be kind of nice to understand when it actually is possible to solve this problem. Okay. So here's the characterization. Turns out this can be done if and only if the so-called permanent of the original matrix is non-zero, in this case positive, because all the numbers involved are non-negative. Okay, the permanent is like the determinant without the minus signs. It can also be written as a sum over all matchings, bipartite matchings. And so indeed, here's another interpretation, namely it's possible to solve this problem if and only if the support of the matrix, which you can think as defining a graph, a bipartite graph, supports a perfect matching. Okay. So it's a beautiful connection between some combinatorial problem, some algebraic quantity, some kind of optimization, and a geometric problem, this matrix scaling problem. Okay. And okay, this may look special, but there's lots of applications to statistics. I gave you one before, to machine learning, optimal transport, complexity theory. I mean, it's a combinatorics problem as we discussed. People use the precondition matrices in numerics, and so on and so forth. And sort of the leading question, sort of ending this appetizer somehow, is 3 questions that we want to sort of discuss in the remaining. So the first one is, why would such a simple, greedy algorithm work at all? I mean, that seems kind of mysterious. Is there a nice explanation? What's the relation between this geometric picture and the algebra, so the permanent, an algebraic function, polynomial? And maybe most interestingly, is there a general picture on all of this? Is this maybe just a special case of a very general phenomenon? Okay. And as far as we know, the answer is yes to the last one, and I want to also indicate answers to the other problems as we go along. Well, what's the general picture? So here maybe now comes an overview of sort of a 10,000 feet overview of sort of this area. So it turns out that actually in a series of works over the past decade or so, many researchers, including us, discovered clues that actually there is a big picture. Lots of problems that seem quite different are connected, and the key ingredients, they seem to be symmetries, okay, as well as this idea of optimization, okay. And these are very diverse kind of problems. So there's theoretical problems in program testing. There's connections to the P versus NP problem that was mentioned. Deep question about de-randomization, which I think we already mentioned. There's algebraic questions about tensors. Maybe Jeroen will say more about that later. Other geometric objects. There's analytic or continuous questions about optimal transport. Actually, I said that the matrix scaling problem can be translated into one. There's applied questions for maximum likelihood estimation, but also theoretical ones. And then there's not only classical questions about classical computation, but also about quantum computation, other quantum features. So that's really sort of a very wide field. And what we are trying to understand in this program somehow is to connect these problems and to find common methods. Okay. And what gives us hope is that in special cases, thanks to the work of Avi and others, we already know that these ideas can be used to find fast algorithms and to obtain new insight. And so the plan for today then is to give you an introduction to these connections on a little bit of a technical level, perhaps too technical, show some applications, and to give you a glance of how optimization curved spaces can help progress, can lead to progress in this area. Okay. It would be fantastic if I would have known when I started. Okay. So let's maybe have a general perspective on this entire area. What's the deal with symmetries? Why do we like symmetries? Okay. And how do we model them in mathematics? So symmetry is right. Two things are symmetric if they look alike. There's lots of ways of formalizing this. One way of formalizing this is via group actions. Okay, so they basically tell us mathematically how to translate, how to convert one object to another in such a way that we would still consider it equivalent. Okay, so here are 2 graphs, but actually they are the same graph, just looked at in a different way. So there's a group action here. And there's a very general problem in mathematics, sort of a meta problem, because it's not really formalized yet. And what it asks is, how can we algorithmically and efficiently check equivalence? And I guess the reason, because I put algorithmically efficient here, that makes it a computational problem, a meta problem, not just, say, a mathematical one. And so this is an interesting problem. It's connected to what we discussed before, and an interesting sort of type of problem. And there's lots of interesting examples and applications. Okay. So graph isomorphism, the problem we discussed above, we don't know how to do as efficiently as we would like to, despite amazing breakthroughs and work. Matrices we know are equivalent, or some of us know they're equivalent if they have the same rank. No idea how to test this for tensors. Okay, difficult problem for tensors. Maybe we'll learn more about that later. When is a polynomial equal to the 0 polynomial? Seems like a very simple question. It's very, if one looks at it in the right way, it's a very deep question and one we would really like to understand. And it would sort of solving this problem without randomness would lead to breakthrough in computer science. And then for mathematicians, there's other kind of motivations why one would like to study symmetries. Okay. Now, so this is a very general setting, very sort of maybe too general to sort of talk about it. So I want to specialize on a situation that seems very harmless and tame to some of us. And it's a problem where we have group actions and orbits. Okay, so I want to discuss to you and explain to you what an orbit problem is. So the idea is that I take some nice group, so a set of transformations, and it's a really nice one. It's a arbitrary invertible matrices, determinant 1, diagonal matrices, what have you. This group acts on a vector space for linear transformation, so we deal with vectors, they're being rotated in some generalized way. And then whenever we have such an action, we can associate it to any point, to any vector and its orbit. So that's just a set of all things that are equivalent to this orbit. Okay. And sometimes these orbits are not closed, so we close them up, so we fill in all the missing points. Okay. Here's a simple example, just a one-dimensional group. It's acting on a two-dimensional vector, scaling the first coordinate by g, and the second one by g inverse. So clearly the product x times y is invariant. So typically these orbits, they look like solutions to x times y equals constant, or y equals, say, 1 over x, right? These are the blue curves. There's also some exceptional orbits, the green one, for example, that say the horizontal axis without the origin, and the origin itself is also an orbit. It doesn't change at all under this transformation. So that's a particular mathematical way of formalizing, okay, and maybe that's sort of as technical as we'll get here. But the idea is just we have some set, we can operate on it, and then we can ask a number of questions. And the most simple one, and the most natural one perhaps is the following: given two such vectors, are they in the same orbit? Meaning, can we transform one to the other? Can we transform one graph into another graph or not? It turns out that in the setting here, everything is continuous, right? We have these continuous objects, and it's very natural to fill in these continuous objects, so to take the closure. So there's two natural ways of making this a robust problem. The first one is to ask, is one vector in the closure of the other's orbit? So basically, can we approximate one point, or one geometric object by a limit of others, okay? And the second one is also interesting. So the first one is not an equivalence relation, right? It's an order, a partial order. The second one is an equivalence relation. It asks, given two vectors, can we transform them into a common third thing? Okay, so and that's another nice problem, and one we would like to study. So now these are actually really hard problems with lots of applications, including the sort of the bubbles I gave on the second slide. So I want to focus on something that's even simpler. Okay, and it's the case where one of the vectors is just a zero vector. And so that leaves us with the problem that we want to discuss in the remainder, called the null cone problem. And what this one asks is basically, I have some arbitrary vector. I can transform it in some way. And the question is, can I transform it as close to 0 as I want? Can I make it as small as possible? Okay, that's called the null cone problem. And we want to sort of, what I want to do in the talk now is I want to give you first sort of a high-level picture why this simple innocent problem relates things that should not be related, algebra, optimization, geometry. And then I want to run you through a bunch of examples and then tell you a bit more about the geometry behind this. So here is the big picture that I want to discuss, and maybe that's sort of the mathy take-home message in a way. So I want to focus on this problem. I have a point. This point defines an orbit and an orbit closure, like in this picture. So this is an orbit maybe for a planet or something. And then there's the origin. That's another point here. It does not change at all under the symmetry. And what I want to know is this origin in the orbit or not. Okay, in this case, it's not. Now, there's various equivalent ways of thinking about this problem. One is as follows. I could ask, for example, I could try to test this, right? And one way of testing is I could take a polynomial, and it's a polynomial that is invariant under the symmetry. So it has the same value when I apply the symmetry or not. Okay. Then clearly, if 0 is in the orbit or in the orbit closure, it will be the case that every such polynomial evaluates to the same value. We cannot distinguish, we cannot test, we cannot tell the 2 points 0 and this vector apart by any invariant polynomial. Turns out that's an if and only if. And now we're suddenly in the world of algebra, where we talk about polynomials. Polynomials have symmetries, invariant polynomials, okay? Which is sort of a very classical field. Again, people like Hilbert did lots of work on that. I guess he did a lot of work in general in mathematics, but also here he's very famous. Okay. Now, there's another perspective, though, which has nothing to do with polynomials, but it's sort of based on the, really like staring at this picture and saying, look, if I want to understand if 0 is in an orbit or in an orbit's closure, well, this is really a geometric problem. What I should do is I should take a point in the vector in this orbit and try to move along the orbit and make the norm as small as possible. So I really want to minimize. I want to minimize the norm. Okay. So that's suddenly we're in the realm of optimization. So what I could ask here, right, is I could say, okay, let's just minimize the norm of this point, this vector v. I apply an arbitrary group element, and now I want to apply the group element that makes this norm as small as possible. Okay, maybe going to 0. So now we're in the world of optimization. Okay, And whenever I have, whenever I have an optimization problem, sort of, and it's a continuous one, the first thing, of course, we'll do is we'll take derivatives. We're going to say, oh, if I'm at a minimum, the derivative must be 0. Right? That's what we do in high school to great success. So maybe it also leads to success here. Okay. So let's do that. Okay. So we could, so here it's a multi-dimensional problem. So the derivative is called the gradient, but it's really the same idea. So instead of minimizing the norm, we could say, okay, let's just look at the critical points. Let's look at the points. So let's try to find a point where the gradient is 0. Okay, this could be minimum, could be a maximum, could be a whatever. Okay, but sort of if we are the minimum, we will be at this point. So clearly, this problem seems simpler than the left-hand side one. Okay, so this problem, the left-hand side is clearly an optimization problem. We're minimizing a norm. The right-hand side, I call a scaling problem, and it's actually the reason is it's exactly a generalization of what we did in the first slide on the appetizer. Okay, we'll come back to this in a moment. But what I want to say beforehand, and what's amazing, is that actually these two problems are equivalent. Okay, so there's some structure, some kind of convexity, which some of you will know, which actually tells us that both of these problems are equivalent. And again, sort of both of these provide us a way of solving this algebraic problem. Okay, so there's sort of a deep connection, and it may seem somewhat technical here, but maybe it looks a bit technical because it's general and because I'm doing a less good job, explaining these concepts. It says a deep connection between optimization, between geometric problems and algebraic problems, and that's exactly what's behind, the bubbles on the second slide, trying to connect all these different fields. Okay. What's very cool as well is that there's also polytopes in the game. So for some reason, everything is continuous here, okay, at the bottom. But for some reason, this continuous problem is actually again related to something discrete. So polytopes appear, difficult polytopes that we would like to understand better. Okay. And so this is sort of the big picture then of this entire program. So somehow we're interested in these problems involving symmetries and group actions and orbits, both for intriguing applications, we'll discuss two in a moment, also because maybe we can actually solve these problems, so we have made algorithmic progress. And actually this is progress not only on this very specially looking null cone problem, but actually on also on the more general orbit problems I discussed on the previous slide. So it provides us maybe the only known path to solving those more general problems. Okay, so that's the sort of the picture. Okay, so this is the problem we discussed at the beginning, the appetizer. How does it fit in with this general story? It turns out, and I don't want to run you through the math, it turns out that this is exactly a scaling problem in this general sense. So the problem of finding, of rescaling a matrix such that it's approximately doubly stochastic fits exactly into this framework if one does a little translation, okay? So it's quite natural that the group should be, a left and a right diagonal matrix, that it should act on n by n matrices. But then one can exactly identify the gradient being 0 with what we want here with double stochasticity. Okay, but I don't want you to look at the math here, so we'll skip over it. The cool thing is that this is not just a translation, but it explains some things. Okay, so it explains, for example, so by this general connection between algebra and geometry, here it explains to us very concretely why should the permanent be related to matrix scaling. Okay, so why is this algebraic problem related to a geometric one? Moreover, the fact that there's this convexity that makes the gradient 0 equivalent to the minimization problem, in some sense explains to us why synchron works. Okay, because synchron's algorithm, this row normalization column alternating procedure, actually minimizes. One can show very concretely it minimizes, something decreases each time. And so but we just discussed that minimizing this function is equivalent to setting its gradient to 0, and that's why it works. Okay. And what is more, again, is that this perspective that actually synchron, even though it does an alternating procedure, it's actually alternating minimization procedure, is really the starting point for more clever, really for the most cutting edge algorithms for this problem, which people are very interested in. Okay. And let's say, well, to put this all into a more general context, it turns out, here the group was very special, was left and right diagonal matrices acting in a certain way. If you look at diagonal matrices acting in a very general way, actually this paradigm recovers very famous paradigm in optimization known as linear programming, or actually geometric programming, which is a bit more general. Okay, so that's kind of cool. Okay, now the question. Actually, can someone let me know how much time I have? Is this like 10 minutes-ish, or?
Go ahead.
Oh, sure, yeah. It's gonna, I guess, be our coffee's loss.
If I stand up, then it's...
Yeah, okay, well, okay. But we'll see. Okay, very good. So this was a matrix scaling. Okay, so very beautiful sort of, almost classical topic by now. And it all relies on symmetries. The symmetries are given by diagonal matrices multiplying on the left and the right. And okay, I come from quantum information, so it's very natural to think about non-commutative things, and it's a natural question to ask, how about if you have non-commutative symmetries? Okay, so surely that will be even more interesting. So the question here is, okay, what would a quantum version of this matrix scaling problem look like? Well, a matrix with non-negative entries is a probability distribution of two variables. So clearly what we want to do is we want to look at quantum states of two variables, of two parties, Alice and Bob. Okay. So a quantum state of two variables is given by a positive net operator on a tensor product. And there's a very natural way of scaling this, namely by the tensor product on the left and on the right. Okay. If you know quantum, then this will be familiar to you. If you don't know quantum so well, you can just imagine that's sort of the natural. We take a quantum probability distribution and we scale its rows and its columns. Okay. That's what we do. And we can define a problem that's known as the operator scaling problem. And it asks us, can we find such scalings such that, you know, afterwards the quantum row sums and the quantum column sums are uniform? That's what we're asking here. Okay. And in fact, one can generalize this problem. It's very interesting to do so. We can say, oh, what more generally, if I start with a quantum state, you know, maybe it's a quantum state of three parties. So it's like a cube, a quantum cube. And I can ask, what are the row sums, the column sums, I don't know, the third direction sums. Okay. I think Harry wants to grab me or tell me it's 10 minutes. Okay. Very good. So this is a problem that's very interesting, for example, quantum information, many other fields. And this is a problem where suddenly polytopes start appearing. Okay. So it turns out that, you know, these row and column sums, if one puts them into, you know, a picture, so this is sort of, you know, the marginals of Alice, of Bob, and of Charlie. If we put them into a picture, suddenly we see polytopes appearing, convex polytopes. Okay. And these polytopes, they're very interesting in quantum information theory. They're interested in algebraic complexity theory, in algebra and representation theory that describe some interesting asymptotic information. So they're very meaningful objects, and they're also very complex objects. In many cases, we can prove they're exponentially complicated. So if you wanted to write down such a polytope, for example, by listing all the vertices, or say the faces, then, I mean, you would take a long time to write them down. Okay. But what's cool here is that they're succinctly encoded. They're encoded in a different way, okay, namely by this group action. Okay. So we can actually write them down very efficiently, but implicitly in this way, right? So what's very interesting to us in this sort of field is, can we somehow reveal these polytopes not by writing down, you know, gigantic lists of vertices or gigantic lists of facets, but actually by giving an algorithm that can check efficiently, is a point in the polytope or not? Okay, so it's a kind of a new or a different one, not new by us, but sort of a different way of looking at, you know, a classical problem describing a geometric body, but of course one that's extremely natural in computer science. And more generally, you know, of course, one can ask, yeah, what are the interesting polytopes that are now captured by the setting, right, by group actions, by symmetries? Can we maybe solve more combinatorial problems by, as it turns out, optimization methods? Okay. So in some sense, you know, can we write another edition of the book where now, you know, we go from convex optimization to this more general kind of convex optimization? Okay. That's, I mean, a dream. Okay. Trying to make little steps. So let's actually talk about this. Maybe I will just very briefly say there's a different, yeah, maybe I should say this real quick, yeah. So there's a different way of looking at the same problem that's about quantum channels, maybe not so important what it looks, I mean, how the formalization works for those of you who are not so familiar with it. But sort of so this is sort of basically, you know, we can think of a matrix as being a joint probability distribution, but also as a channel from one side to the other. So there's the same setting in the quantum case. And there it turns out that there's a beautiful alternative characterization. Okay, so if we package our starting state, you know, in a different way by a tuple of matrices, then it turns out that this operator scaling problem that we discussed before, so row and column sums or quantum row and column sums of a quantum state, now can be described in a different way. Namely, the scaling problem has again an algebraic characterization, and it can be solved if and only if this funny object is non-zero. Okay, so we're given a bunch of matrices xk. And now what we're doing is we're sort of looking at a linear combination of these matrices, but it's not really a linear combination. We're adding a tensor. We're tensoring with some other, you know, auxiliary matrices alpha. And if you can find such matrices such that the resulting matrix is invertible, then and only then can this operator scaling problem be solved. Okay. And so you can think of this as sort of, you know, a symbolic matrix that's now a matrix in non-commutative variables. And if this matrix in non-commutative variables has non-commutative full rank, okay, so it's invertible in this sense, then and only then can this operator scaling problem be solved. And the thing I wanted to say is that actually if you restrict this problem, if you don't allow arbitrary matrices here, but just numbers, then this is just a linear combination of some fixed matrices. It's a symbolic matrix. Then actually checking if such a symbolic matrix is generically invertible, it's very easy to do randomly. You just pick random alphas. And we don't know how to do efficiently deterministically. Okay? And that's, of course, a big motivation here. And interestingly, this non-commutative problem, thanks to a result by Avi, can be solved in polynomial time, deterministic polynomial time, importantly. Okay, so this problem here. And one dream, again, maybe in this larger program, is to connect this actually to the commutative version, to this commutative version that's known as the polynomial identity testing problem in theoretical computer science. Okay. Again, so I gave you two motivations, quantum and TCS, polynomial identity testing. There's lots of other connections, analysis, operator algebras, statistics, and so on that I don't want to go into. But sort of, again, it's sort of a very universal problem, it appears. Okay. So there's lots of more problems. I don't want to talk about them, but we can just marvel at the colors of the slide and maybe the diversity of the fields. Some of you will know some of them, others, I guess. So that's from some geometry, combinatorics, optimization, of course, quantum problems, classical problems. As I mentioned before, here it's a bit of a more technical list. In some case, some of you want to see a bit more explicitly that that it was not just bragging on the second slide, but indeed there's some content, okay, between these connections. So the last couple minutes I want to use on giving you, as promised. So now I guess we made through the first two parts, right? We have some applications, we have sort of a general framework. I want to give you a glance of like what it all has to do with again, optimization, convexity, and so on. So I want to discuss how all these things are related to optimization on funny spaces and curved spaces. So what we want to do is we want to minimize this function, right? We want to minimize the norm because that's what was this null problem. We want to know, can the norm go to 0 or not? Okay, I'll take the log. I like logarithms. Okay. Now this problem, it's say the group is a GLN, so invertible matrices. Now any invertible matrix has a polar decomposition. We can write as a unitary times a positive definite matrix. Unitaries don't change the norm. Okay, if one sets up things in a reasonable way, sort of by definition. So it's enough actually to do this optimization over the positive definite matrices. Okay. Positive definite matrices, there are a nice set. We can think of it as a subset of Euclidean space, but you can also think of it as a nice curved manifold. Okay. And it's a nice manifold. It's very symmetric. It's called a symmetric space even. But one interesting thing is it's not flat. It's not flat unlike Euclidean space, but it has non-positive curvature. Okay. Okay, sure, we can do that. We can also use this change of variables to define the gradient. Okay, we can define the gradient of our function simply by taking the gradient with respect to x. Okay, and then we can make more precise what I said before, that setting the gradient to 0 captures these scaling problems. Okay, just as an aside. But what is sort of the geometry of this function, of this norm or log norm function? If you take this geometry seriously, okay, if you really say, okay, we want to think of the positive definite matrices as a curved manifold. It turns out that in this case, it's not a convex function in ordinary sense. So it's not a convex function of the matrix G. It's also not a convex function if you write G as e to the x in X. But what it is convex in, it's convex along curves. It's convex along the geodesics, the sort of the straight lines in this, well, non-straight, in this curved manifold. Okay. So whenever you pick a direction inside this, funny space we had before, say this one, then our function will be convex. Okay. And so this is a more general notion of convexity. It's not the Euclidean notion. It's a more complicated one. It's more local in some sense because you don't have global. It's just along lines, but along arbitrary lines. So it's somewhere in between, right? Like knowing nothing and knowing nice global convexity. But it's so powerful enough, for example, to show that derivative equals 0 means we are actually the minimum. Okay, and that's, for example, something that we like. Now, to develop this into an algorithm, to use this, so the good thing about convexity is it gives us hope that we can solve these problems efficiently by an algorithm, right? Whenever things are convex, that's usually, things like gradient descent would work, at least heuristically, okay? But if you actually want to analyze an algorithm, you need to know a bit more. You have to sort of know how convex it is, right? For example, is it not too bandy? Okay, that's called smoothness. Or you want to maybe know if my gradient is small, am I close to the optimum? Okay, maybe some of the machine learners in here, they think deeply about such questions. So that's something we figured out, and maybe I will skip this. So there's some nice inequalities relating these two sort of sides. And I maybe just want to sort of end on sort of summarizing maybe the state of the art of this framework before sort of summarizing sort of the talk. Okay. So this was the setting I explained to you before. So we have a general symmetry given by some group, model acting linearly in a vector space. we started with this very innocent problem. Can we distinguish the vector from 0? Is my vector equivalent to the 0 vector or not? Okay, like the simplest problem you could imagine. Okay. Turns out that one good way, and maybe the only general way, we know that, well, I guess the only sort of one very natural way of attacking it is by thinking of this as an optimization problem. We simply minimize norms over the orbit. By this duality that we can make quantitative, okay, we can relate this to well, saying, oh, the gradient should vanish, so that seems boring. But actually, often this is now an extremely interesting problem, such as matrix scaling, operator scaling, other kind of scaling problems. Turns out that in many applications, actually, the starting point is on the right, and we kind of have to reverse engineer what is the symmetry. Okay, that's why sometimes we think that the symmetries are sort of hidden inside these computation problems. Someone gives us a problem that only in hindsight can be put into this framework, but once we do, we manage to solve it, or at least we have a new way of attack. So it turns out all the examples I gave before in the list that we didn't read, that we weren't supposed to read at least, fall into this framework in one way or another. The fact that there's this convexity, it explains why a local greedy algorithm can work. We can quantitative, okay, by something we like to call noncommutative duality. It's a sort of a noncommutative generalization of duality as one knows it from ordinary convex programming. And then there's also, first algorithmic progress, okay, on this line. And now Harry comes to punch me, but it's okay, because we are going to go to skip. I mean, we discussed algorithms. We don't care about these. You just want to summarize. Yeah, Harry's a scary person. So what I want to communicate, okay, is three things. So one is that behind problems from algebra and analysis, 2 ones in classical, even quantum computer science, as we saw. Sometimes there's polytopes popping up in mysterious ways, polytopes we would like to understand, but that are very complicated to describe directly. So we would like to describe them, algorithmically. And how can we find such algorithms? Well, again, symmetries are key. They tell us what are the spaces that we should be optimizing over. They guide us towards, this hidden notion of convexity. And they also give us the tools, in this case, from invariant theory, to tackle them and to find efficient algorithms. Okay, and so there's lots of exciting questions here. I mean, it's the start of a journey, and I'm very grateful sort of to have been a little part of this journey together, with Avi and sort of the whole group, whole gang. And yeah, so thanks a lot for your attention.
Thank you, Michael, very much. I allow one question, and then we run outside. Peter.
Thank you. Concerning this world of polytopes, you mentioned that algorithms exist to determine whether a point is inside or outside. Are there also algorithms for establishing the identity between two polytopes?
That's a good question. So I guess you could think of this in a general setting, or you could think about, I guess, in the case here, right, where you have sort of 2 points, each implicitly determine a polytope. Are they the same polytopes or not? I don't have a good answer. I mean, I've wondered about similar things. I mean, also, yeah, indeed, kind of say, yeah. I mean, I guess it's a very classical theory that tells you once you can decide whether a point is in a polytope or not. You can do lots of other things, but I'm not sure about this particular one, to be honest. That's a great question.
Thank you.
Yeah.
Okay,